we're looking at L, which is an operator on P3. And the way it's defined is that you give it a polynomial, and then it gives you back the derivative of that polynomial multiplied by x plus the second derivative of your polynomial. Okay, so for example, if we take L of x squared, well, it'll say, I'm going to give you back your derivative multiplied by x and add on second derivative, right? So you get 2x squared plus 2, what it'll give you back. And the question we're looking at is, what is L100 of 3x plus 5 plus 5x squared, right? And so, you could do this, the slow way. How would you do it? One way to do it would just be to apply this operator 100 times. So you take the derivative, multiply by x, add on the second derivative, you get something, take the derivative of that, multiply by x, add on the second derivative of that, and do that 100 times, right? So that's one way. The easier way is to, the problem has a few parts to it. First is to find the matrix representation of L with respect to the basis 1x squared, right? And since we kind of did this already, let's just talk about it, right? How do you find the matrix representation of this guy? Remember, it'll be a 3 by 3 matrix. How do you find the matrix representation? Anybody remember? Yeah, can you guys do it? Connor, how about you?
You just take turn the A1 vector.
You take the elements of the basis, is what you want to say? Yeah. And then what do? You take each element of the basis, right? You got x1 and x squared, and then Kevin?
Do you multiply by like I think I did 2 matrix 1 0 0 0 1 0.
No. Remember, remember the setting here, right? You've got vector space from here to here. You've got your basis. You got your basis. The bases give you your coordinate vector maps, right? And then you construct the matrix representation. Remember the columns of the matrix representation. I guess we call it T in our first presentation. Right, the columns of the matrix representation are just, you take the elements of your basis. You take the elements of your basis, and then you take your elements of your initial basis, right, your domain basis, and then map them over through the linear transformation, and then take the coordinate vector with respect to the second basis. Okay. Right. So here we would take the elements of our basis. We're using the same basis on both sides here. We take L of 1 and express it with respect to the b basis. We take L of x with respect to the b basis, and L of x squared, and we take its coordinate vector with respect to the b basis. Right. Okay. Maybe I won't rush through this too much since people are. It's not completely clear to people. Okay, so L of 1, right? That's going to be 0. So if you take first derivative and second derivatives, those are both zeros. Right? Right. L of 1, right? You take your polynomial, take its first derivative, that's 0, multiplied by x, that's still 0. Take the second derivative, that's 0. Right? So you get 0 with respect to the b basis. Well, the coordinate vector of 0 with respect to the b basis is just going to be 0, 0, 0. Right? L of x, well, that's you take the derivative, multiply by x, take the second derivative, which is 0. Right? So you get the coordinate vector of x with respect to the 1 x squared basis. So that's going to be 0, 1, 0. Right? L of x squared we did already. It's 2x squared plus 2. With respect to the b basis, well, that coordinate vector is going to be 2, 0, 2. So that gives you the columns of your matrix representation with respect to that basis. Okay. Okay. Everybody all right? Okay. So we have our L, we have our matrix representation, right? Here it is, right? So one way of answering our question would be to say, well, instead of doing by hand my operation L 100 times, I can do it more automatically. I've got my 3x plus 5 plus 5x squared. I'm going to map it down here to the Euclidean universe, right? And I get the vector 5, 3, 5, right? I get the vector 5, 3, 5, and then if I want to get L 100 times, well, that's the same thing as multiplying by in the alternate universe, right? It's the same thing as multiplying by the matrix 100 times, right? So I take my matrix 0, 0, 2, 0, 1, 0, 0, 0, 2, take it to the 100th power, and multiply 5 to 5, 3, 5 by it, right? And you get something, and then you would come back up here, and that would tell you what your polynomial is, right? That would be actually be a lot better than doing it this way, right? Right. That would be a lot better than doing it this way because you just need to multiply your matrix 100 times, right? Rather than have to think every single time, what's going on here. Right? So Okay. But there's an even better option, which is to use a different basis. So we have a basis b prime. Out of nowhere, we pull this basis, which turned out to be really good. Basis b prime, 1x, 1 plus x squared. Yeah, comment.
Sorry, where did we get that?
Out of nowhere.
I don't know.
Yeah. Okay, so exercise 2, find, for practice, the transition matrix S b prime b. Find S b prime b. Because if we want to get the matrix representation with respect to b prime, we're going to use S b prime b and conjugate by it. Conjugate our original matrix, our original ABB matrix by it.
So it's going b prime to b.
Yeah. Yeah. Find the matrix that goes from b prime to b. Right? Because that'll allow us to get the AB prime b prime matrix. So how do we get it? Right, S, how do we get the S? Right, if we're going from B prime to B, what do we need to do? Somebody?
Take the coordinate vector with respect to the coordinate vector of B prime. These are expressed by as a linear combination of.
Right. So we're going to take each of the guys in B prime and express them in terms of the B basis, right? So this is going to be just 1 plus 0 the other guys. This is 1x. This is 1, 1 plus 0x plus 1x squared, right? And then we use those coefficients. 1, 0, 0, 0, 1, 0 as the columns. Right. Those are the columns of our transition matrix. Okay. Right. And then you could, you could find A, B prime, B prime, B prime by conjugating, right? By using this, using that guy and conjugating our first matrix by it, right? Okay. That's actually more of a pain than doing it the direct way, right? So if we find A, B prime directly, right? B prime is 1 plus x squared, right? You say, okay, well, let's apply L to 1, L to x, and L to 1 plus x squared. This turned out to be 0, this turned out to be x. This, if you work it out, turns out to be twice 1 plus x squared. Okay. And then to get the columns, oops. Right? To get the columns, you take the coordinate vector with respect to B prime. Well, what's that? This is going to be 0, 0, 0. This one's going to be 0, 1, 0. And what about the last one? 0, 0, 2. 0, 0, 2. Right? Okay. So our matrix, right? Our matrix is this guy, right? 0, 0, 0, 0, 1, 0, 0, 0, 2. Right? Right? And if we come back to our problem here, we say, okay, right? Instead of using B, we use B prime. So we would multiply by A and B prime to the 100, right? So we would take this guy and then take its coordinate vector with respect to the B prime basis, right? Well, its coordinate vector with respect to the B prime basis is 0, 3, 5. Right? Because the B prime basis, right, is 1 plus x squared, right? And this is 5 of this guy, 3 of this guy, and 0 of that guy, right? There's only one way to express it. Okay. So you get 0, 3, 5. Is that clear, Connor? No. Right? We're taking. Remember, we start off with this polynomial. We want to hit it with our operation 100 times. So you take this guy and you take its coordinate vector with respect to the B prime basis, right? Well, this is 3x plus 5, 1 plus x squared.
Right.
right? So I take I have 0 ones, I have 3 x's, and I have 5 of this third vector, right? And then I want to multiply it by the matrix 100 times. But this is great, right? This is, this is a diagonal matrix, right? So that was 0, 0, 0, 0, 1, 0, 0, 0, 2 to the 100th power, right? But it's a diagonal matrix, so when you multiply, you're just multiplying by the entries, right? Okay. So when we multiply this guy, it's easy, right? And we end up with 0, 3, 2 to the 100 times 5. Yeah, Mariah?
Wait, so why would you find the transition matrix?
We didn't need it. Yeah.
Okay.
It was just to remind you of how to do it. Yeah.
And like, what if A, B prime, B prime wasn't diagonal?
Yeah, then it wouldn't really help you that much.
Yeah.
Right? The whole point of this is that, if your matrix is diagonal, then things become really easy. Right? The point is that with a good choice of basis, right? With a good choice of basis, your matrix representation could be a lot simpler. Okay. We'll get back to that in 1 second. But let's get back to here. So we see that in the Euclidean universe, the answer is this, right? That tells us that in our original universe, the answer is 0, 1 plus 3x plus 2 to the 100 times 5 of 1 plus x squared, right? So this is our answer. Okay. So doing this 100 times, doing the operation 100 times to this vector, to this polynomial, actually easily calculated. Okay. So of course, it's pretty clear which way you like to do it, right? You don't like to do it the first way. Nobody would want to do it the first way. Nobody would also. The second way is certainly better than the first way, but the third way is the best of all, right? Any questions about the procedure? Okay. Yeah, sure.
Just about diagonal matrices.
Yeah.
So the product of like two diagonal matrices is just the product of between the diagonal entries.
Yeah. Yes. Okay. Okay.
Is it usually not that easy to find A, B prime directly?
Right. So how did we get B prime? Right. How did we get B prime? Or better, what was good about B prime? What was good about this basis B prime? What made B prime a better basis? And what was good about B prime? What do you see about 1x squared that's better than 1 plus x squared, sorry. What was better about this basis than the other basis? What was so good about it? Well, we got the diagonal matrix, right? What about it made the matrix diagonal? What about this basis? What's the property of this basis that makes you have a diagonal representation?
Each term can be represented by only one term.
Yeah. So.
Wait, isn't that true of the other bases too?
There's two over there.
Yeah. So you've almost got it, Tara. Each of these, when you take L of 1, well, let's look at L of x. So L of x is x, which is just one term. But more than it's just one term, yes.
It's multiplication of itself.
It's a multiple of itself, right? it's not one of the other terms. It's actually itself, right? Or it's represented by some multiple of itself, right? So, right. So you look for a good. I erase the line. You're looking for. Right. The point is that. With a good choice of basis, the matrix representation becomes simpler. Right? Now, what's good? Good means, in this case, what is good? What is good? Well, in this case, it means that if your basis looks like B1 at the end, say, good means that when you hit each guy with the operator, then it becomes a multiple of itself. Right? That's what good means for us, right? Right. If we have a basis that acts like this, then the matrix representation is going to be diagonal. Right. These guys have names. This sort of quality is given a name. Right. We say that Bi is an eigenvector of L. Bi is an eigenvector of L. Okay, with eigenvalue alpha I. So this one is an eigenvalue with eigenvector with eigenvalue 0, right? It turns into 0 times itself. This guy is an eigenvector with eigenvalue 1, right? It turns into 1 times itself. This guy is an eigenvector with eigenvalue 2, right? When you hit it with the linear transformation, nothing too strange happens to it, right? It just turns into twice, a scaling of itself. And this is what we'll spend a fair amount of time talking about in chapter 6. Okay, any questions? This is basically the end. Yeah, Ethan.
I'm just trying to make sure.
Yeah.
So each, you basically came up with that basis, the new one, basically just to simplify the matrix representation of L.
Yeah, exactly. So we started off with one basis. That first basis gave us this matrix representation.
Right.
Okay. But then we had this other basis we pulled out of nowhere, basically, the second basis, and that basis had a much simpler representation, right? So you should be asking, like, how did we pull that basis out of nowhere? We'll talk a lot about it once we get to chapter 6. It would make sense to sort of jump into chapter 6 at this point, but we'll take a sort of a detour and then get back to it. So this is the end of matrix representations for now. Okay, but we'll come back to it in some sense. Actually in chapter 6 we'll basically ignore matrix representations and just deal with matrices. Okay, but in the back of your mind you have this knowledge that if you have any linear transformation, you got its matrix representation, right? So if you want to understand the matrix, if you want to understand the linear transformation, well, you can go to a matrix representation and hopefully try to get a simple one. Okay, So yeah, in some sense, we're saying goodbye to matrix representations, but you should keep them. Don't forget what the point is, right? To understand linear transformations. Okay. So now we're going to go into chapter 5. Chapter 5 is something to be. The title of chapter 5 is inner product spaces. Okay. Inner product spaces. This term inner product is basically a generalization of something called the dot product. Right? The dot or scalar, also called the scalar product. So everybody close your eyes for a second. Close your eyes for a second. How many of you have not seen the dot product before? Okay. How many of you have not seen projection before? Vector projection? Okay, great, thank you. Okay, so let's, I think much of this section, much of section 5.1, so section 5.1 is the dot product in Rn. Okay, and I think much of this it will be reviewed for you. Okay. So I think everybody knows if you have these two vectors in Rn, we think of them as column vectors, then their dot product is defined as the sum of the products of the corresponding components. Right? You have these two vectors, right? X1 through xn, y1 through yn, right? And then you take the products of the corresponding components, and then add up all those products, and that's a dot product. Right? You've all seen this before. We will write this as the product of the transpose of t against y, because that's what it is, right? You take the transpose of x against y, because you take this thing and you multiply these two guys as matrices, and you get a 1-by-1 matrix with this as its entry. Okay. As usual, we're going to continue conflating 1-by-1 matrices and numbers. Okay, so it's true this is a 1-by-1 matrix and this is a number, but 1-by-1 matrices for us are basically numbers. Okay. So that's the dot product. Okay. The magnitude of a vector, right? So if you have x in Rn cross 1, what's the magnitude of it? How do you define the magnitude? You all probably seen this before. So how do you define the magnitude of a vector? Anybody? Too easy? Embarrassed to say it? Mariah, go ahead. Thank you.
Factor, that's not the factor, we square it.
Yeah, basically. Right, so you get x1 squared plus x2 squared plus xn squared to the 1 half. Right? Which is the same thing as the dot product of the vector against itself to the 1 half. Okay? Just to work in the dot product. Right, we have the magnitude of the vector, like geometrically. It means, of course, right, the distance of the terminal point, like here's your vector, is the distance of the terminal point to the origin, right, or just the length of the vector. This thing called the distance between two points. So if you have one point in space and you have another point in space, and you want to find the distance between them, you take the magnitude of the difference. So the distance between x and y we define as the magnitude of the difference. Right? So you have your x, right? You have your y. You take x and add on to it minus y, right? And that gives you this vector here. And this is x minus y, right? Well, the magnitude of that is this distance here, right? And this thing has magnitude x minus y. Right? That's the distance between these 2 points. Okay. Right. So you see that the dot product. Once you have a dot product, you can have a notion of size, and you also have this notion of distance. Okay. Number 4, geometric interpretation of the dot product. Turns out that the dot product has a geometric meaning. Does anybody know it? What does the dot product mean geometrically? It's actually...
I forget.
You forget. There's some cosine involved.
Yeah, something to do.
Right. So it's the product of the magnitudes times the cosine of the angle between them. Product of the magnitudes times the cosine of the angle between them. And the proof of this is to use this picture that we have up here. Right, we've got, this is x, this guy is x, this guy is y, this guy. So this is length, this guy has length x, this guy has length y, this guy has length x minus y. Okay, and here's our angle theta. Okay, and so you use the law of cosines, which is basically like the Pythagorean theorem for any triangle. The law of cosines says that, well, c squared equals a squared plus b squared minus 2ab times the cosine of the angle between them. Okay, so this is going to say that c squared equals a squared plus b squared minus 2ab cosine c. Right. Just apply the law of cosines to this triangle here. Yeah, Lieutenant.
Sorry, could you define again what C stands for in that?
C is the angle between in the law of cosines, so A, B, C, C is the angle opposing the side C. Okay, so here it's the angle between the two vectors. Okay, so then you just work this thing out, and it gives you the geometric interpretation, right? You say, okay, well, look, this thing here I'm going to write as the dot product of x minus y against itself, right? This thing on the left is the square of the magnitude. We know that the square of the magnitude is the dot product of the vector against itself. Right? Okay, so that's going to be x dot x minus 2x dot y plus y dot y. Right? These guys are equal. Right, these guys are equal, right? But then you say, okay, well, x dot x is the same thing as magnitude of x squared. Y dot y is the same thing as magnitude of y squared, right? So you see that negative 2x dot y is the same thing as negative magnitude of x times magnitude of y cosine theta. Okay, divide by negative 2. Okay. Okay, so that gives us what we said, right? That the dot product is the same thing as the product of the magnitudes times the cosine of the angle between them. Everybody all right? Any questions? It's just a consequence of the law of cosines. The law of cosines is a consequence of the Pythagorean theorem. Pythagorean theorem we proved on the first index. If you want to entertain yourself, if you've got nothing to do in class right now, you can prove the law of cosines from the Pythagorean theorem. It's just for entertainment. Okay. Okay. A consequence of the geometric interpretation is something called the Cauchy-Schwarz Inequality. Cauchy-Schwarz Inequality, which says something very simple, that if you take the magnitude, if you take the absolute value of a dot product, well, that's smaller than the product of the magnitudes, Okay. But that's obvious because you know that the magnitude of the dot product is the absolute value of the dot product is the absolute value of this thing. Right? But this thing is this, right? And the absolute value of the cosine is smaller than 1, right? This is smaller than equal to 1, right? So you know that the absolute value of the dot product is smaller than this. Okay, this will not be too useful, but it will show up here and there. Actually, I mean the Cauchy-Schwarz inequality in general is like something that shows up all over the place in mathematics. There's a book called the Cauchy-Schwarz Masterclass, and it's just devoted to an entire book of different ways of interpreting the Cauchy-Schwarz inequality and proving it. Yeah. So I mean, it's not that this is unimportant, but it's only going to show up once in a while for us. Okay. Okay. Number 6 is definition. So if the dot product is 0, we say x and y are orthogonal. Orthogonal is just another word for perpendicular. Okay. And you see why this makes sense, right? Because if the dot product is 0, at least if your vectors are non-zero vectors, then that means that the cosine is 0, right? Well, the cosine being 0 means that they must be perpendicular to each other. Okay, so that's why we use this as a definition. Number 7, we call the vector divided by its magnitude the direction of x, or the unit vector in the direction of x. Because it's a vector of size 1. It's a vector of size 1 with the same direction. So like, if this is your unit circle, right, and this is your x, then this guy is your x over its magnitude. We also call it a normalized vector. Normalized vector. Okay, so we're just sketching out some ideas which most of which you've seen before. So the last one is one that some of you haven't seen, number 8. So the vector projection. Vector projection of one vector onto another vector. So x onto y. Okay, so the idea is like this, right? You have one vector y, and you have another vector x. Okay. And you want to find out, you want to basically break x into 2 pieces, one of which is parallel to y, and the other of which is perpendicular. Okay, so you want to break x into this guy plus this guy, right? Or another way of saying is you want to see what this guy is here. And once you know what this guy is, you know what the other guy is. Okay. This thing here is called the projection, the vector projection. People usually just say projection. The projection of x onto y. So you think, okay, well, here's this angle here, right? Here's this angle of phi here. Okay. So I know that if I have this length, let's call this length L, right? I have this number here. I know that adjacent over, right? I know that the cosine of phi is the adjacent over the hypotenuse. calling this length L. It's the adjacent over the hypotenuse, right? So what do I know about, how do I figure out what L is? Well, I know what the cosine is, right? The cosine of phi, I know that L is going to be L over the magnitude of x, then is going to be the cosine of phi. Well, the cosine of phi is x transpose y, x, y. Right? So that tells me that this number here is x transpose y over the magnitude of y. Okay. That's a number. That's not a vector. That's a number. Okay. This number is called the number is called the scalar projection of x onto y. Okay, if you want to give it a name. Most people just ignore it. But if you want to give it a name, it's called the scalar projection. Right? So that's just the number here. To get the vector, well, we have to multiply that number by the normalized y vector. So we take our y vector, right? We take its normalization, that'll give us some little direction here. We multiply that guy by L, and that gives us the vector projection. Okay, so the vector projection of x onto y is the scalar projection times the normalized y vector. So that's how you get the vector projection onto here. And you get the scalar projection, and then multiply the normalized y vector by it, and that gives you this vector. Okay, that gives you this vector. Notice that you could, right? So this thing here is a number. This is the normalized vector. Sometimes people write it this way. They'll write it. They'll move this out and get the magnitude of y squared on the bottom, and so it looks like you could write it like this if you felt like it. Okay, you move the magnitude of y over here, you get the magnitude of y squared. Magnitude of y squared is the dot product of the vector against itself. So that's one way that some people sometimes express it. I like this way better because it's more clear to me. Right? You're taking the scalar projection, and multiplying it by the direction vector. Sorry, I kept you a few minutes every time. Okay, that's it for today.